Hello, class. Since I couldn't be in class today, I've recorded a lecture about population ecology, and my anticipation is that you will be listening to this lecture in class. You'll be taking good notes, following along as I prompt you, and then after class, you're going to go back to my website. Remember, on ChristopherLannis.com. Under Unit 2, there will be a form, a Google form, that will be called Population Size Form. Your job will be to complete that form before Wednesday's class. Today's lecture is about populations. We started talking about populations last class, and in this lecture we're really going to be talking about population ecology, specifically how we determine population size, and through a method known as sampling. Okay, so that's what we're talking about today. Keep in mind we've already talked about community ecology and ecosystem ecology. First things first, let's define population. In ecology, the term population refers specifically to an interbreeding, so let's underline that. It's an interbreeding group of the same species, let's underline that, of organisms living in the same area. Let's underline that as well. So please take that note, please take that definition into your notes. An interbreeding group of the same species of organisms living in the same area. In these pictures, we see examples of populations. In the top left-hand corner, we see a population of penguins. Again, this is a population because the penguins are of the same species. They are living in the same area, and because they are the same species and living in the same area, they are capable of interbreeding. The same can be said of this population of wolves, this population of salmon, and even this population of oak trees. However, let's also keep in mind that this population of oak trees is a single population of oak trees, but it doesn't refer to all of the oak trees worldwide. It only refers to the oak trees, say, for example, in this forest. So there might be a population of oak trees in this forest, there might be a population of oak trees in another country. Many different populations of oak trees, for example, make up the entire species of oak trees. Keep in mind, populations are defined about the species in a specific area or location. And in order to be able to study populations, one aspect of populations that is important to study is the size of the population. Many times the size of a population gives you information about that population. How healthy it is, does it have natural predators, is it being controlled, or is it being limited in any way? So it's very important in population ecology to be able to determine population size. And on the next slide, we'll give you a quick example of something like that. What we see here are a bunch of dots and on a particular kind of graph. Let's imagine that these dots represent oak trees, and the graph itself represents a forest of oak trees. What I'd like you to do is to tell me how many dots are in the forest, or how many oak trees are in the forest, rather. However, you have one limitation. Instead of just, the only limitation you have is that you may not simply count all of the dots. What I'd like you to do in your notes is I'd like you to develop a plan or develop a strategy to estimate the number of oak trees in this forest. In your note, please describe what you would do, or how you would count, or how you would sample this image to estimate the number of oak trees. Pause the video for a few moments to allow yourself some time to take some notes and to develop a method. Now what I'd like you to do is to share with a partner your estimation, and I'd like you to share with your partner the method by which, or the strategy by which, you use to estimate how many oak trees are in this forest. Pause the video and share with a partner, please. Now there are several ways or strategies. There are a number of strategies that you may have employed to estimate the number of dots in this image. One strategy you may have used is maybe instead of counting all of the dots in all of the rows, maybe you chose one row and you counted the dots in that row. And then you said, oh, there are 10 rows, so let's just take my answer and multiply by 10. You may have done something similar, except instead of using rows, you used columns. And you counted all of the dots in a single column and said, oh, there are 10 columns, let's multiply my answer by 10. These are great ways of sampling, or these are great ways of estimating using a sample of the entire population. I'm going to give you one more strategy, a very similar strategy compared to the rows or the columns sampling, and we're going to call it random sampling. Random sampling is a method of sampling a larger population where we randomly count a subset of the larger population, and if that subset, if it's random, should be representative of the larger population. That means proportionally it should represent, if you counted 1/10 of the population, or 1/10 of the size or the area of that population, it should represent the entire population. It should be 1/10 of that entire population. The goal here, of course, is to pick a random sample. And if we look back at the oak tree example, or that oak tree graph, picking a single row or a single column may or may not be representative. It may or may not be random. Maybe, for example, a single row might have a larger proportion of dots in that row than another row. So maybe a single entire row might not be representative of the entire population. My suggestion instead would be to select 10 random single boxes. Instead of entire columns or rows, you'd select single boxes and count 10 random boxes and use those boxes as your random sample. So let's take a look at how we would do that. In order to take a sample and calculate from that sample the entire population size, we're going to use a certain formula. So make sure to write this formula in your notes. The equation that we'll use, or the formula that we'll use, is that you'll take a sample, the number of organisms that you've chosen in that sample, which will be the subset of the population. That sample will be represented by the lowercase n. And you'll take, given the volume or the area that you collected that sample from, that will be lowercase v. That will be equal or representative or proportional to the total population, which will be capital N, over the total volume or the total area, capital V. So what we have here is n divided by v is equal to capital N divided by capital V. And if we wanted to solve then for our total population, we would multiply both sides by the total volume of our area, or the total volume of, or the total area of, for example, our oak tree forest on both sides. And what we are left with is capital N is equal to lowercase n times capital V divided by lowercase v. In other words, we take the sample times the total volume or area of your habitat divided by the volume or the area that you collected. Let's take a look at an example here. Now I'll work an example for you. So coming back to that oak tree forest that we saw. All right, let's take 10 random boxes. Let's take this box here. Let's take this box here. Let's take this box here. This box, that's 4, 5, 6, 7, 8, 9, 10. Okay, and let's count our total population here. We see 1, 2, 3, 4, 5, 6, 7, 0, so still 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Our sample, or lowercase n, is equal to 18. We know that this total volume, capital V, is equal to 100 boxes. So we're going to say it's 100. And we know our sampled volume is 10 boxes. And so we're looking for total population. N equals lowercase n times capital V divided by lowercase v. And so let's take 18 times 100 is 1800 over 10. And our total answer then, of course, is, and I'm running out of room, so is 180. So our estimation, or our given our random sample, our estimation is that there is about 180 oak trees in this oak tree forest, for example. So we're going to take a look at a couple more examples and work out a couple more problems together. Before we do that, let's ask ourselves the question, when might random sampling be a good strategy to estimate population size? Secondly, I ask you the question, when might random sampling might not be a good strategy to estimate population size? Pause the video, take a few moments to jot some notes down into your notes. Okay, and share those thoughts and share those ideas with a partner, please. All right, so we can talk about several good situations or positive situations that when random sampling might be a good idea. One situation is certainly when the population size, the size of the population, is just too large to count itself, too big. All right, a second good reason, or a good situation for random sampling, is when there is an even distribution. An even distribution of our organisms in a particular area. All right, because if our population size is too big, that means we're not going to be able to count each and every one. So random sampling lends itself very well. Additionally, when our population is evenly distributed, taking random samples, taking a subset, will, by definition, be representative of the entire population. So if we take the opposites of these, when our population size is small, it would not make sense for us to perform a random sampling exercise. And secondly, if our population is not evenly distributed, that is to say, if there is, for example, some kind of clumped distribution. So let's imagine a particular forest where we're trying to sample certain kinds of fungus, and let's imagine that a certain fungus is only located at the very center of the forest. I don't know. And if we're trying to randomly sample this fungus, and we take samplings all around the forest, that might not be very representative if all of the fungus is located in the center of the forest. That wouldn't, if in a clumped distribution of organisms, random sampling will give us a not a very accurate or precise measurement. And finally, let's take a look at a couple problems. First problem, in a forest that is 51 square kilometers big, or the area is 51 square kilometers, you go about and count oak trees in a random sample, and you count 100 oak trees in a sample space of 3 square kilometers. That, which is to say, maybe you walk around a forest and you spot an oak tree here and an oak tree there, and you have sampled in areas of 3 square kilometers. So we have some information here. We have our sampling size, which is 100 oak trees. We have our sampled space, or sampled volume, is 3 kilometers squared. And our total volume, the total size of our forest, is 51 kilometers squared. And we can plug this into our equation, where we say our total our total population size is equal to the sample times our total area divided by our sampled area. And we have, let's see here, 100 oak trees times 51 square kilometers divided by 3. After you perform your calculation, you'll calculate that there are 1,700 oak trees, if I can spell correctly, oak trees in our forest. That is our estimation. It might not be exact, but it gives us a pretty good image, or a pretty good picture of how many oak trees there are thereabouts. And here's a second problem. In a small pond that is 3,000 liters in volume, you count 14 salmon in a sample volume of 100 liters. How many salmon are in the pond? All right, I'm not going to work this one out for you. I'm going to ask that you do this one for homework. Both the last problem and this problem will be found on the Google form that you are to complete, along with a few definitions and other questions about this lecture. So take the rest of the time, take the rest of the period to work this problem out, making sure that your notes are satisfactory. And the Google form will be, again, on my website and is due before Wednesday's class. All right, thanks, guys, and I'll see you Wednesday.